Welcome back, everybody. Okay, so section 5.2 is called the definite integral. The definite integral. The whole chapter 5 is called integrals. We don't even really know what that is yet. You kind of do. You've done one. You've done two. You did two on the quizzing stream. But we don't really understand what it is yet. We don't really know how to compute it. We don't really know what it is. So a lot of today is going to be, definition and things like, okay, what are the basics about this thing? Okay, we saw in section 5.1 this limit, right? This is the as n goes to infinity of the sum of a function times its delta x, where each time I plug in xi, that's like the end point of an interval that I can find the height for, which will give me a rectangle, right? So this is the limit as n approaches infinity of an infinite amount of rectangles, area of an infinite amount of rectangles. That's really what this notation is saying, right? And then we're thinking, okay, is there a way that I can kind of summarize this? Like, is there a way that I could write that a little bit easier so that we can work with it a little bit more, so it's a little bit more manageable, right? We also saw that it arises when we try to find distance traveled by an object. Turns out that the same type of limit occurs in a wide variety of situations. Basically, the Calc 2, if you go on to take Calc 2, it's a lot more, it pushes more into integrals and the applications of integrals. Right now, we just kind of scratched the surface a little bit. But there are, you can go even further into this stuff. Now, this is what's going to be the definition of an integral. The definition of an integral. So if f is a function defined between a and b, we divide the interval ab into n subintervals of equal width. That's exactly what we did before, right? We're taking that interval and we're dividing it into equal intervals, delta x, where delta x is b minus a over n. And then we let x equals 0 be a, and then x1, x2, x3, x4, xi up to xn, right? And xn is b. We divide it up in there. Be the endpoints of those subintervals, right? And there are any sample points in those subintervals. So xi lies in the I subinterval. So this is our definition of our definite integral. Now, there are going to be two types of integrals. Sections 5.2 and 5.3 deal with the definite integral, and section 5.4 deals with the indefinite integral. Okay? Section 5.2 and 5.3 are the definite integrals, and then 5.4 is the indefinite integral. The definite integral says, basically, I have endpoints. I have a solid boundary from one point to the next, and I want to find the integral from a to b. So understand that process of finding the area, that process of finding the area underneath a curve is the process of integration. That process is finding the integral of that function. And that's how we say that. You find the integral of an equation, and if that is saying I'm finding the area underneath the curve along that interval. Now here's the notation that we're going to use. Okay? Here's the notation. The notation basically, and I think I kind of talk about it a little bit more in depth on the next slide, but the notation basically says that's kind of like an elongated S. That's where that symbol came from. S for sum. Okay, this notation says that I'm going to find the sum from A to B. Right? Those are the endpoints. This is the definite integral. When it's an indefinite integral, when I don't know the boundaries, those are left blank. So you just see the curve there. And that's saying, okay, find the area underneath the curve of some sort of function. Now, this is the integral of, and right next to it has to be some sort of function. We're going to call it just f of x, right? That will be where the function that you're trying to find the integral of comes in. So that could be the integral of sine of x. That could be the integral of x squared plus 4x plus 2. That could be the integral of the natural log of x, right? That's where you'll see the function, right here, right? Then, and this is just notation. This is just notation. This doesn't actually play a role yet. You're going to see a dx. Okay, you're going to see a dx. The reason that is there is because one, it references, look, dx and delta x, right? It references that you're going to be using like the differential on x, like the delta x, right? The change in x. It's not f of x times dx. Be careful with that. It is not. I'm not going to be like multiplying anything. That is just notation there. Okay. This looks a lot like our length times width, right? It looks a lot like that, but it's just there to reference back the fact that this area, I am going to be using my differential on x. It's also there to define, like sometimes our functions don't necessarily have just one variable, or that could happen. It could happen that we have more than one variable within our function, and this references what we are going to take the integral with respect to. Like remember when we did implicit differentiation, we had a couple different variables and we were always going to be taking, we had to know what we were taking the derivative with respect of. Like usually it was x. But there was y's in the equation. And we knew that by saying, okay, I'm going to take d over dx of the function, saying I'm going to find the derivative with respect to x. And that was the notation, d over dx. This is saying, okay, that will tell you what variable I am using. So if there's multiple variables within that function, I'm going to find the integral with respect to whatever that is, right? Call it dx, call it dt, call it dA, whatever it may be. That variable in there, that dx, that means x is what I'm going to find the integral of, okay? I kind of said a bunch of this stuff already, but the symbol, this symbol was introduced by Leibniz. It's called the integral sign. He's also the guy that introduced this symbol, this notation. That's the Leibniz notation for derivative. This is the Leibniz notation for the integral. It's an elongated s, and it was chosen because the integral is a limit of sums, s for sums. In this notation, the f of x, that little piece in there is called the integrand. This is just formalities. This is called the integrand, whatever I'm finding the integral of. And a and b are the limits of integration. A is the lower limit, b is the upper limit. For now, the symbol dx really doesn't have any meaning by itself. It's all symbols. It's all symbolic. It's just really noting that it's an x that I'm using. The actual procedure is called integration. And you can call functions, and I should have said this too, you can call functions, I don't know where the emphasis, like what syllable the emphasis is on. Is it integrable? Or, no, it wouldn't be integrable. That'd be integrable. Integrable, we'll say that. You can call a function integrable. It doesn't sound right. Integrable? Integrable. Emphasis on the in. Okay. It would be on the A. Integrable. No. Integrable. That sounds like I'm from Texas. Is that function integrable? But that is the property of the function, because some functions are integrable and some are not. Just like some functions we could find the derivative of and sometimes you couldn't. The same idea, okay? And this is just saying we could change up the notations, right? We could change up the variable inside there, but that would also change the variable outside here with the d, okay? Other things to see here. I've talked about the Riemann sum a little bit, and we've done Riemann sums. You actually did two on the quiz yesterday, right? We did a left side Riemann sum and a right side Riemann sum. The Riemann sum is just basically the sum of all of those rectangles, right? The sum of all of those rectangles. That's really what a Riemann sum is. Something that we have not done thus far, and this is the reason why I have this page on here, is that sometimes you might have areas that go below the curve. Sometimes you can stretch below the curve and above the curve. Above the curve would be a positive area. Below the curve is a negative net area, okay? So you can have positive areas and negative areas. I know we normally would say, oh, you can have a negative area, like back in geometry, we would say that. But in this respect, you can. You're just going to dip below the x-axis, okay? So we have positive areas, but we could also have negative areas as well. That does happen from time to time. What else did I want to say up there? What was that note? Riemann sum, blah, blah, blah. Up here. Yeah. Okay. Yeah, this kind of summarizes everything in there, how it relates to the Riemann sum. Just the differences in the notation, right? This is kind of what we already wrote down, but a lot of what today is just figuring out how to use and how to read this notation, right? Figuring out that, okay, if I've got this notation, if I'm given this, how do we interpret that? Right? Because it really is equivalent to the Riemann sum, the sum of the areas from A to B, knowing that delta x is b minus a over n, of f of x dx, knowing that f of x is f of xi, and xi is a plus I delta x. See, the nice thing about this notation is that you would need all of this for that little notation. All of that is equivalent to that. We can see every single piece I've boxed in yellow in here. And that's what's nice about the integration notation, the integral notation. The fact that I can see all of that stuff in there. Like all of this is taken care of with the knowing what an integral is. The dx is referencing it, the delta. We know that delta x is b minus a over n, right? And this is saying, well, I don't really have to say n because if I know that n is going to go to infinity based on the fact that I know what this symbol is. Okay. All right, so let's do it. All we're going to do is take this and express it as an integral. We're going to take this and express it as an integral. I am not really going to do anything with this. All I'm going to do is just change the notation. Okay, that's it. Just going to change the notation. So I've got this function. Do we see the function inside here? Oh, that's yellow. Do we see the function inside there? So what I'm going to do is I'm going to take out the pieces that I need. Oh, and I know from 0 to pi, right? I'm going to take out the pieces that I need and put it into the integration notation. So I do my funky looking elongated S. I put the lower boundary on the bottom and the upper boundary on the top. So I go from 0 to pi. Next comes the function. Okay, we take out the i's now. X to the third plus x sine x. And right next to it would have been our delta x. We're just going to write dx. Yeah. If you want to put it in parentheses, you can, but honestly, it's kind of understood that you don't need it there next to that dx. It's not like you would be just taking the dx or the x sine x or something like that. You see how simple that is? Lower boundary, upper boundary, function dx. And that is telling you, we can read that as the area underneath this curve, whatever that looks like, whatever that is, the area underneath that curve from 0 to pi. If I were to draw it out, figure out net area underneath that curve toward the x-axis. I think I want to do this next. Okay, now, evaluate the Riemann sum for x to the third minus 6x, taking sample points to be the right endpoints. A equals 0, b equals 3, and n equals 6. And then I am going to evaluate the integral from 0 to 3 of x to the third minus 6x dx. Understand that those two things are actually asking you the exact same question. I am asking you to perform the exact same operations, the exact same answers. The difference is A is an estimate and B is an exact. A is going to be an estimate. I'm going to estimate the Riemann sum. I'm going to find the Riemann sum, which is an estimate of the area. And then part B, I'm going to find actual area. I'm going to teach you how to do that. All right, let's take a look at A. Evaluate the Riemann sum for f of x is equal to x to the third minus 6x, taking sample points to be the right endpoints. So we're really going to find this, R6, right? I'm going to find R6. Okay, so for that, I need to find delta x. Well, delta x is b minus a over n. So 3 minus 0 over 6, 3 over 6. is 1/2. 1/2 comes up a lot. Just because it's easy. It's easy for me to make problems like that. So we got 1/2 as my delta x. Again, I like to have my delta x on the outside here. And then I'm going to find each of my y values as I go, right? Now, what is the first y value that I have? Now, think about it. Am I going to be using a as one of my y values? No. Remember, hopefully we've seen a pattern with right endpoint, left endpoint, and whether I use my a value or not. If I have right endpoint, if I'm using right side estimation, right, that means that this first point that I have is not going to be used. It's the end of the interval that is going to be used. Like if I were just to make a crude sketch of this thing, I don't even know what it looks like. Whatever, it doesn't really matter. And here's A, whatever, what B is over here, sure. If I want to find that first rectangle, I am not, and I want to use right endpoints, like where, if this is the right side of it, where am I going to go over here? No. I'm going to take my next, the end of that interval, push it up there, and that's the y value that I'm using. No matter where the other, wherever the rest of it ends up, that's the right endpoint. So for right endpoints, x1 is going to be 0. Sorry, not 0. Oh, actually, it is 0. 0 plus I delta x. So 1 delta x. 0 plus 0.5. Right? 0.5 times 1, I guess you could say. And then x2 is going to be, well, the next strip. So 0 plus 2 delta x. And we can kind of see where this is going. I just need 6 of them. So I'm going to find f of 0.5 plus f of, well, each strip is 1/2 in length. So f of 1, f of 1.5, and so on. I just want to make sure that I'm not getting ahead of myself. Yeah, good. Okay. So here's f of 1. Let me get this weird diagram that doesn't really mean anything over here out of the way. And then 1.5, and then 2, and then 2.5. Oops, f of 2.5, and then f of 3. How do I know I stopped there? 2 reasons. How do I know I stopped there? That's the end point, first off. Second off, I want 6 strips. 1, 2, 3, 4, 5, 6, right? There's 2 reasons why I end there. I know that I've got 6 rectangles that I'm trying to find, so I should only have 6 y values. And the other reason is the fact that that is the end point. I'm going to 3. Don't go beyond 3. Okay, so let's find each one of those. Now, this is going to take some calculator work here because the function is a little weird, right? I think you can probably tell that the more difficult the function, the more difficult it is to find the Riemann sum, right? The more difficult the equation, okay, that's going to be a little bit more difficult. So we've got 0.5 to the third minus 6 times 0.5. Okay. Negative 2.875. Let me just make sure I'm plugging that in right. 0.5 to the third minus 6 times 0.5. Okay, good. And then I'm going to add, okay, we got 1 to the third minus 6 times 1. Plus, I'm just adding all of these y values, right? 1.5 to the third minus 6 times 1.5. Plus, now I'm going to do 2. 2 to the third. Whoa, be careful. 2 to the third minus 6 times 2. Plus, and then we've got 2.5 to the third minus 6 times 2.5. Plus, one more, 3 to the third minus 6 times 3. Okay, that is all my y values added together. So it's half of all of that times 0.5. Negative 3.94. Negative 3.94. That is what R4 is. How is it possibly negative? What is this telling me? The fact that that's negative, what is that telling me about the graph? That most of it from 0 to 3 lies underneath the x-axis, right? Or there's a bigger amount of area underneath the x-axis rather than above the x-axis. What's wrong? Did I have a whoop? What'd I do? Oh, sorry. Thank you. I'm just so used to finding R4. We found R4 like so many times, didn't we? Oh. Well, there's always 20 more. Yeah. I know. R6, negative 3.94. Now, that's an estimate, correct? Do we know whether this is an over or under? Not necessarily, because I don't know what the function is going to look like. I guess I could go in and graph it and really be a little bit more precise about it. But again, the functions that we were looking at were always decreasing or always increasing, so it was really easy to tell whether it was an overestimation or underestimation. This one looks like it went up and down based on what the calculations we're looking at. So I don't really know whether this is an overestimate or underestimate. I know it's probably pretty close, but if I wanted to get closer, I would just have to do more strips, right? Okay, now, you want to hear for the fun part today? What am I talking about? All this stuff is fun, right? We're having a blast here. We're eating donuts. Okay. If I wanted to evaluate the true value of the integral, the true value of the integral from 0 to 3 of x to the third minus dx, or minus 6x dx. I had said earlier on that there must be some way that this antiderivative must play a role. Like we talked about it a little bit in the, in referencing the distance versus speed, right? We could find total distance by just having speed. Well, the speed is the antiderivative of, the distance is the antiderivative of speed, right? Derivative of speed is distance, so distance is the antiderivative of speed. So there must be some way, if I was able to find, during this process, if I was able to find total distance given speed, there must be some way that the antiderivative plays a role, right? Take a look at this here. If I wanted to know the integral from 0 to 3 of x to the third minus 6x dx, okay? If I wanted to find that integral, what I can actually do is set that equal to the antiderivative. What is the antiderivative of x to the third minus 6x? X to the fourth over 4 minus 6x squared over 2 plus c, right? And then I want to evaluate that antiderivative only on a given interval, right? Here's the notation. Here's what the notation looks like. It's a vertical line stretching above and below, where the top number is the maximum limit and the bottom number is the lower limit, like the lower limit than the upper limit. Now, what is this telling you to do with this thing? I know I can simplify that 3x squared. But what is this telling you to do with this thing? Well, this vertical bar is find the difference between those values. Find the difference between 3 and 0. Find the difference between 3 and 0. So what does that mean? That means I'm going to take 3 to the fourth over 4 minus, and I'm just going to evaluate that 6 over 2 to be 3. 3 times 3 squared plus c. Okay, we're going to leave that in here for a second. Minus, I'm going to find the difference between these two things. Find the difference between 3 and 0. 0 to the fourth minus 3 times 0 squared. I should say over 4. Minus 3 times 0 squared plus c. That vertical bar just says find the difference between. Okay, so let's actually evaluate that. 3 to the fourth. What is 3 to the fourth? 81, right? 81 divided by 4. Minus 3 times 3 squared. So 3 times 3 squared is 27. And so I have negative 6.75. plus c minus, well, isn't this and this 0? Right? Isn't 0 to the 4th over 4 minus 3 times 0 squared? Isn't that all just 0? Right? And then we take this plus c. We are very off on our... Oh, well, yep, minus c. Hold on. Yep. Oh, wait, no. No, I had that right. I just forgot my parenthesis. Yeah. Because when I distribute that parenthesis, what happens to my c values? They cancel. Womp, womp. Negative 6.75. Now, why am I so... 81 over 4 minus 27. Did I forget to divide something? Or is it just that far off? No, I guess it's just that far off. So here's what I get. You know what this is? True value of the area. True value of the area. So how far off really was I? I was almost like 2 points off. Right? More than that, almost 3 points. That's the true value of the area. This is how you evaluate actual area underneath a curve. So it connects with the antiderivative. Okay? It connects with the antiderivative. We'll push forward into this more tomorrow. This more gets us into section 5.3. I kind of mesh sections 5.2 and 5.3 a little bit. Hey, get another donut if you want to.